Okay, today we're going to be looking at number sets. Okay, and we're going to be talking about the real number system. Okay, now this consists of every single number you know, but we've got to be able to put them into their categories. Okay, the first category, something that you probably already know, is whole numbers. Okay, now whole numbers is only the positive whole numbers. Okay, the positive numbers that you're used to seeing, like 0, 1, 2, 3, and so on. And the next is integers. And integers are positive and negative numbers. Okay, but still whole numbers, like -3, 6, 0, 18, -25, the square root of 64. Now, hold on. Is the square root of 64 an integer? Yes, because the square root of 64 is 8, and that's an integer. It's actually a whole number as well. Okay? So then the next number set is called rational numbers. And we've already talked about those as well. And if you remember, they're numbers that can be written as a fraction. Okay, numbers like 1/4 or 0.2 or 0.5 repeated. Okay, remember, anything that's not a decimal is rational. And any decimal that stops or repeats is also rational. So the fact that this decimal stops here, 0.2, makes it rational. The fact that this decimal repeats, 5 repeated, makes it rational. And then the last subset of numbers is irrational numbers. And those are just numbers that cannot be written as a fraction. And that's numbers like pi, the square root of 5, or 0.04225, ... Okay? So, now, I will point this out. Notice, here's our square roots. This is where most irrational numbers come from, is square roots. Okay? Now, of course, if it's a perfect square, then it's going to be an integer or a whole number. But if it's a square root of something that's not a perfect square, then all of those are irrational. So that's where most of our irrational numbers come from, are square roots of non-perfect squares. Okay? Now, let's think about these whole numbers. Since whole numbers are positive numbers, and integers are positive and negative numbers, then all of our whole numbers are also integers. And since all whole numbers and all integers can just be written as that number over 1, like 6 over 1, -25 over 1, then that means all of these can be written as fractions. So all integers are rational. Okay? So this is one subset here. Everything that's a whole number is also an integer, and everything that's an integer is also rational. Now, it doesn't go the other way, because you can see 1/4 is not an integer, and -25 is not a whole number. Okay, but all whole numbers are integers, and all integers are rational. But then irrational is just kind of by itself. Okay, So these are all separate. If something fits into any of these categories, then it cannot be irrational. And if something is irrational, then it cannot be any of these. Now, all of these together, whole numbers, integers, rational numbers, irrational numbers, all together make up real numbers. Okay? So this is your real number system. These are all the numbers that you know up to this point are real numbers. Okay? Now, and we're going to do a little bit of a graphical display of this that will kind of demonstrate it a little bit better. Okay? So, draw this along with me. Okay? First, you need to draw this on your paper. You've got a big rectangle cut into two smaller ones, but the one on the right is smaller than the one on the left, so that you have room for these two circular figures, ovals if you will, okay, inside the one on the left. Okay. Now, in the small circle here, these are your whole numbers. Okay, they're whole numbers like 0, 1, and 2. Okay, are all in this circle. So all your whole numbers, 76, 812, they're all in this circle. Okay? Well, in the larger circle, we have integers. Okay? Well, notice, the whole number circle is inside the integer circle because all whole numbers are integers. But there are some things that are in the integer circle that aren't in the whole number circle, like -6, -3, negative square root of 25. Now, is that an integer? Yes, because square root of 25 is 5, so -5 is an integer. Okay, so some integers aren't whole numbers, but all whole numbers are integers. Okay, then in the larger box, we have rational numbers. Now notice, all whole numbers and all integers are inside the rational box because all of them are rational. But then again, there are some things that are rational that aren't integers, like 1/4 and 0.2 repeated and -7.5. Okay? None of these are integers or whole numbers, but they are rational. Okay? And then in our other box over here, we have our irrational numbers. Now notice, there's no overlap between irrational numbers and any of the other types of numbers. Okay, they're completely separate. And this would be numbers like pi, square root of 5, and 0.04225, ... going on forever without repeating. Okay, and like I said before, the entire box, the whole big box, is all of our real numbers. Okay, so this is our graphical representation of our real number system. Okay, everything in the whole entire box is a real number. Everything in this part of the box on the right is an irrational number. Everything in this box on the left is a rational number. Everything in the bigger circle is an integer, and everything in the smaller circle is a whole number. So some numbers can be more than one subset of numbers. Okay, you could have a number that's just rational and real, or you could have a number that's an integer and rational and real, or a number that's whole number and integer and rational and real, or irrational and real. Okay? So, that's what we're going to practice next. We're going to identify the subset of numbers. Alright, so you've got 5 numbers here, and you need to tell me which sets that these numbers belong to. Alright, so let's look at the 4. Okay? If you look back at your chart that we just drew, the 4 is definitely a whole number. Okay, because it's positive and there's no decimal or fraction, so it's a whole number. Alright, but whole numbers are also integers. And integers are also rational. Right? Oh, and rational numbers are all actually real too. Correct? Now, this point forward, I'm not going to really put real on everything because everything is going to be real, right? Every number that we know is real. Okay, so I'm not going to put real every time, even though all of these numbers are real. Alright? So now, looking at the next one. Negative 7 over 2. Okay, well I already know it's not a whole number because it's negative. Okay, now, but is it an integer? Well, 7 over 2 is 3.5. So that's not an integer. Alright. Okay, but it obviously can be written as a fraction because it is, so it must be a rational number. Okay? And that's it. It's rational and it's real. Okay? Now the next fraction, negative 36 over 4. Okay, again, I know it's a negative number, so it can't be a whole number. Okay, it's written as a fraction, so it's obviously rational. Alright, now is that it? Well, be careful, because I can simplify negative 36 over 4. Doesn't that just equal negative 9? Because 36 divided by 4 is 9. So negative 36 divided by 4 is negative 9. And negative 9 is an integer. That means negative 36 over 4 is also an integer. Okay? Sometimes you may have to rewrite it to be able to tell if it's an integer or a whole number. Okay? Alright, now looking at the decimal. 0.555 dot dot dot. So it's just the 5s repeating. Well, it's not a whole number. It's not an integer because it's got a decimal. But it's a repeating decimal, which makes it rational. Okay, and again, all of these are real as well. Okay, now, the square root of 3. Like I said earlier, this is the main time you see your irrational numbers. If you're taking a square root of something that's not a perfect square, is 3 a perfect square? No, it's not. 1 is, 4 is, 3 is not. That means if you take the square root of 3, then you get an irrational number because you would get a decimal that doesn't repeat and doesn't stop. Okay, now we have to determine which is larger, okay, or be able to put them in order. Okay, so I've got 2 numbers here, the square root of 17 and 4.2. I need to be able to tell which number is bigger. Well, I can't compare these like this because they're not the same, they're not written the same way. So what I'm going to have to do is put this in my calculator and figure out what it is as a decimal. When I do that, I get 4.12. Well, now it's easy to tell which one's bigger because now I'm comparing 4.12 and 4.2. So obviously 4.2 is bigger than 4.123. Okay? Now don't get tricked. This isn't 123 should be bigger than 2. Remember, you look at the first decimal place. The only reason to look past that is if they were exactly the same. Okay? So 4.2 is bigger than 4.1. Okay, so that would be my answer. So here's your steps. Step number 1, when you're trying to compare numbers, is make them all decimals. Okay? And step number 2, then you can compare looking at the place values in order. Okay? Whether you have fractions, decimals, square roots, it's always easier to compare them as decimals. So make them all decimals, and then you can compare them. Alright, now, this time, you're going to put the list of numbers in order from least to greatest. So this time you're not just comparing 2 numbers, you're comparing 4 numbers. And you got to know which one is the least, all the way up to which one is the greatest. Alright, so I'll give you a minute. Remember the steps that we just talked about and see if you can put these 2 number sets in order from least to greatest. Okay, now the first step was make them all decimals. Okay, so looking at number 1, 2.71 repeated is already a decimal, so I can leave that. 2 3/4, I need to write that as a decimal. That would be 2.75. Okay, because 3/4 is 0.75. Okay, then square root of 5, I put that in my calculator. Okay, oh well, I did this one first. 5 over 2 is 2.5. 5 halves is 2.5. Okay, and then I need my calculator for this one, square root of 5, because I can't approximate on these because I need to know exactly. Now this one I probably can, because I can tell that this is just barely bigger than a 4, so it's barely going to be bigger than 2, so it's probably just 2.1. Okay, so, and the others are a lot bigger than 2.1. See, this one's 2.5, 2.75, 2.71. I know that the square root of 5 isn't closer to 3 than it is 2. So 2.1 is good enough in this case. Alright, so now I have my 4 decimals to compare. 2.5, 2.1, 2.75, 2.717171 repeated. Okay, so the smallest is the square root of 5. Now notice, I didn't put the 2.1. because that's not the number I'm trying to order. I'm trying to order these numbers. So you have to use these numbers in your final answer. So the square root of 5 is the smallest because that was 2.1. Then 5 over 2 because the 2.5 was the next smallest. Then 2.71 repeated. Now I used that one because that's the one I started with. And then the biggest was 2 3/4. So that's my answer for number 1 in order from least to greatest. Alright, and number 2, I'm going to do the same thing. I need to make all of these decimals. Okay, so I put this in my calculator. And square root of 11 gave me 3.317. So negative square root of 11 is negative 3.317. These two are already decimals, so I just have to change this one to a decimal. 16/5 is 3.2, so negative 16/5 is negative 3.2. And I have my 4 decimals. Now, you have to be careful on this one, because since all of them are negative, it could get a little confusing on which is least and greatest. Because something being more negative is less than another number. Okay? So the smallest number here is not the 3.2, because negative 3.2 is bigger than those other numbers. The smallest number is negative 3.4 because it's the most negative. And then the next smallest, I have 3.3. Okay, well, this one's 3.33 and that one's 3.31. Okay, so 3.3 repeated is the next smallest. Okay, and then the 3.4 317, but that's not what I started with, so I have to use this, negative square root of 11, and then the biggest number is negative 16/5. Now, this may look confusing because it looks like they're ordered from greatest to least, but because of the fact that they're negative, this is actually least to greatest. Alright, and the last thing that we're doing today is actually solving equations with squares. Alright, so now we have squares inside of an algebraic equation, and we have to solve them. Here's an example of a simplistic one. We just have a squared equals 36. Okay, now some of you probably already know the answer to that. Okay, but let's talk about mathematically how we find it. Okay, first we need to go back and think of our inverses. What's the opposite of plus? Yeah, it's minus. What's the opposite of multiplication? Yes, it's division. And the other day we talked about what's the opposite of squaring something, and that's taking the square root. So these are our inverses. This is how you get rid of things algebraically. If you have addition, you use subtraction. If you have multiplication, you use division. If you have a square, you use a square root. So I'm trying to get the a by itself, right? Algebraically, that's how we do it. So I have to get rid of this squared. So what do I use to get rid of a squared? Oh yeah, a square root. So I'm going to take the square root of a squared, but if I take the square root of one side, yes, I've got to take the square root of the other side. Okay? Now, what is the square root of a squared? Well, didn't we just say that squares and square roots cancel each other out? Yeah. Because think about it, if you square 3, you get 9, and if you take the square root of 9, you're back to 3. Okay, so the square root of a squared is just a. They cancel out. Okay, and what's the square root of 36? It's plus or minus 6. Now, some of you might be saying, well, I didn't see this sign up here. Okay, well, let me draw them in. Okay, now, why do those have to be there? Okay, first, because I'm taking the square root. Okay, look at the problem. There's no square root sign in the problem. So I don't know which square root sign I'm supposed to use. Okay, if you don't know which square root sign you're supposed to use, you have to use the one with all the solutions. Okay? Because if I just pick the positive or just pick the negative, then there's a solution that I didn't find. Because there's two solutions to this equation. A could be 6 or A could be negative 6. And if you don't pick both of them, then you missed one. Okay, so every time you're solving an equation and you take the square root, you have to take both answers. Okay, the good rule of thumb is if you're the first one to write the sign, you have to use this sign. Okay, notice this sign wasn't in the problem. I had to add it. So if I have to add that sign in there, I have to use this sign. Okay, now typically when I write this, I don't put the plus minus sign, but I know it's there, so when I do my answer, I always have my plus minus. Okay, so that's the solution to a squared equals 36. A could equal positive 6 or negative 6. Okay, now let's look at one that has more steps. We have the same thing. This is just an algebraic equation. We've got two things to get rid of this time, a minus 1 and a squared. Well, if you remember the math truck, you've got to unload them on whatever comes last. So obviously I'd have to unload addition and subtraction before I did exponents. So I've got to get rid of this minus 1 first. Well, how do I get rid of a minus? With a plus. So I add 1. And that gives me x squared equals 9. Well, now that looks like this one again, right? So to get rid of the squared, I've got to use a square root. I've got to do it to both sides. So the square root of x squared is x, and the square root of 9 is plus or minus 3. Again, like I said, you won't see me write this plus or minus because I know it's there, and I'm going to write it here. Okay, if you want to go ahead and write them in like this, that's probably better. Okay, so that's my solution, plus or minus 3. Because if I plug in a positive 3, that's 9 minus 1 is 8. If I plug in a negative 3, that's 9 minus 1 is 8. Okay, so let's look at our steps. Our steps to solving equations of squares. Step 1 is get the square by itself. So if you have any extra stuff like the minus 1 or a times 3 or a plus 5 or anything else extra, then you got to get rid of it first. You got to get the square by itself. Then you've got to square root both sides. Notice, once the square is by itself, we took the square root of both sides. Once the square is by itself, we took the square root of both sides. That's the only two steps. Once you take the square root, you'll be done, as long as you had the square by itself. Alright, now let's see if you can do some. So you're going to try to solve these equations. Alright, so you've got 5 equations to solve, and I'm going to give you a minute to work them out. Alright, now, number 1 is pretty straightforward. Just like the example, we have x squared equals 225. The x squared is already by itself, so I'm just going to take the square root. Okay, the square root of both sides, so that gives me x equals, and we should know the square root of 225, and that's plus or minus 15. Okay, number 2, the square is not by itself yet, so I'm going to have to add 4 to get rid of it. Then that gives me x squared equals 25. Now the square is by itself, so I can take the square root and I get x equals plus or minus 5. And that's the solution to that equation. This one has a times 2. How do we get rid of a times 2? With a divided by 2. So I divide both sides by 2. That gives me x squared equals 100. Now that the squared is by itself, I can take the square root and I get x equals plus or minus 10. For number 4, the square is already by itself. Seems like this one's going to be pretty easy. So I take the square root of both sides and I get x equals, but wait, this is no real number. Why is it no real number? Because that's a negative 4 under the radical. You can't square root a negative number. We did that yesterday. Okay, you always have to remember the rules that we've done because they could pop up anywhere. Okay, so if you try to take the square root of a negative number, it's always no real number. Okay. All right. So then, let's look at number 5. The squared is already by itself, so we can take the square root. All right. So square root of x squared is x. Oh, but this time, this isn't a perfect square. That's okay. We know how to estimate estimate squares that aren't perfect. Okay, we find the perfect squares around them. The square root of 49 would be a little less. The square root of 64 would be a little more. So that means that I'm looking between 7 and 8. And 50 is a lot closer to 49 than it is 64. So I'm going to estimate this at 7.1. So this is my solution to number 5.